enough for filters. Let's now look at two-port circuits, which is chapter 18. And now you know we have to put on our 2-year-old hat and ask why. Why two-port circuits? How many are taking 351C or have already had 351C? Have you had hybrid parameters? H parameters? What? HFE, for example, H sub FE. Have you seen that floating around? That's this guy. Or you could see two-port parameters, the H parameters, hybrid parameters. We're going to focus on Z parameters, but what we are doing is trying to collapse down or simplify a complex circuit into maybe 4 parameter values, or describe some piece of a subsystem or a circuit by 4 parameters. Meaning, if you have a complex design, it might be easier just like eating an elephant, right? One bite at a time. You break it up into smaller pieces. So that's what we're doing here. We're simply breaking up this complex design into smaller pieces, and these smaller pieces might be sizes or chunks of two-port circuits. It might be easier to attack the design in pieces. Meaning, we might have a design where we have maybe a photodetector. And we want that when it responds to maybe drive an actuator. But it can't, a little photodetector is not going to be able to move a big electromechanical actuator. So we may have to do some signal processing and amplification to make that happen. Meaning we might have to amplify this small signal coming from the photodetector with a preamp. We might not be wanting to dance around with every little signal that the photodetector detects. And now maybe we put a low-pass filter in there. And you know now how to build low-pass filters of any order, of any complexity, especially Butterworth. Then we might want to, boy, I'm going to run out of paper width, but you know how I solve that problem. Now we might have to power that up in order to drive this actuator. Instead of having to worry about building all of this up in one big piece, we could think of each of these 3 little subsections or sub-circuits in terms of its 2-port parameterization. And now we simply have to design a low-pass filter. We simply have to design a preamp. We now have to design a power amp. And then we put all of these pieces together, and they sing very well together, so that we can now respond to whatever that photodetector is measuring and driving this actuator. What are these things called 2 ports? Two ports, schematically or as a picture, look like what we are stating they are. We now have this system or circuit, and it has a port on the left, which we might call the input port. We have currents going in and the same current actually going out, I1, and we might have then a voltage across those two terminals, V1. And that might, in some particular system, be representative of an input. We could also then, or conventionally, we have I sub 2 going in from the right to the left, and it also needs to come out of that port. Meaning here is our input port, the 1s, and the 2s with subscripts are the output port. And we might have 1,000 transistors and R's and C's inside that S, and we're collapsing all of that down into maybe 2 parameters that characterize this system in terms of these 2 ports, an input port and an output port. That's what we're wanting to do, and all we are really wanting for now is to be concerned with the terminal or the port behavior. We're only interested, we've now designed it the way we want it or the way we like it, and now we're only interested in the terminal or the port behavior. With respect to 2 ports, we have actually some restrictions which, when satisfied, allow us to play with 2 ports. One is we do not allow any energy stored in the network. No energy stored, so we don't have any batteries in there. We can have energy storage elements in here, but no energy stored within the network. Basically no active, or well, I shouldn't say that. No, let's just think of it as no batteries inside that subsystem. We also are not going to allow any independent sources. So we don't have any function generators inside that big block S. No independent sources. Within the network. But dependent sources are allowed. The diagram already illustrated this, but our currents, if it goes in to the top terminal, it has to come out the bottom terminal. So our current into a port must equal the current out of that same port. And you might hear this referred to as the port current requirement. And finally, if we interconnect this 2-port with something else external to it, all of these external connections are made to either the input port or the output port. All external connections are made to either the input port or the output port. Those are our restrictions or constraints to allow us to use these concepts of having a two-port, and you don't have to worry too much about those, but that's just something to keep in mind for later. In this particular description, how many variables do you see? Oh, so don't double count. If I have an I1, don't count it twice if I have it up there twice. How many unique variables do I have? 4. And we are going to allow 2 of those to be independently selected. We have 4 variables, and 2 of those we will allow to be independent. That means for a 2-port, we really only need 2 equations to describe the behavior of that circuit. Because we're going to have 2 independent variables, 2 dependent variables, and we only have the 4. So now we have 2 equations that are going to be governing this behavior. We have 2 equations are needed for the different possible interrelationships that we might have. So if you're looking at your textbook sometime, page 680 is where 6 of these 2-port equations are listed. We have Z parameters, those are impedances. We have our independent variables are the currents I, and the dependent variables are our voltages. So that's like having an impedance there between the currents and the voltages. The second set, equation 2, is the reciprocal of that. We have voltages as inputs and currents as outputs. So those are our admittance parameters. The first ones were our impedance parameters. And you can walk down through this. The second or the third set looks like you have all of these output port variables, the V2 and the I2, driving or determining your input parameters. And those are like transmission parameters from the output transmitting back to the input. Similarly for 4, now we're going from the input transmitting up to the output. And you might see these kinds of parameters in like a 381 class, for example, an electromagnetics class. There's the H parameters, and that's a hybrid. It's mixing input current and output voltage to drive input voltage and output current. And then you have sort of its twin or its complement in the G parameters. Those are the different configurations. We are going to be concentrating on those, the Z parameters. So you don't have to have all of these memorized. You just need to know what's going on, and that's the one that we are going to be looking at. So hopefully you didn't stress out by trying to write all of those down in the short amount of time that I gave you. Let's look at some examples, trying to derive these or find these for particular circuits, which is what you will need to be doing on the homework and on the final. Here is a particular structure that might be called a T-network. It's now called that because of the way it's physically structured. It looks like a T. Here is now our variables that we have defined for the different locations of current and voltage. And if I1 is flowing there, and let me go ahead and label these resistor values, we have a 1, a 3, and a 2. We could think of these currents, I1 and I2, as somewhat like mesh currents. They're not going to be flowing in the same direction like you typically want to define mesh currents, but you really have this current is I1 and this current is I sub 2. Is that okay? Meaning the current going down through that middle path is a combination of the input and the output current to give you I1 plus I2. What we want to do is find the Z parameters for this particular T network. And if we remember what we just saw in that list of equations, the Z parameters say, oh, that relationship is V1 is Z11 I1 plus Z12 I sub 2, and V sub 2 is Z21 I1 plus Z sub 22 I2. And the indices or the subscripts on your Z's hopefully are somewhat clear. The second one is saying, what are you taking? And the leftmost one is saying, where are you going? Or input and output. So Z11 is the impedance between I1 and V1. Z sub 1, 2 is the impedance between I2 and V1. All right, if you had to analyze this circuit, how would you do it? Just a normal circuit problem. And in this case, V1 might be potentially a signal source. There might be a source there, so you could sort of view that as having a supply in V1. And V2, that might be an open circuit. It might have a load attached to it. It might be a short circuit. And so you're measuring these V1 and V2 potentially in a given configuration. But now we want to find equations that, and in another setting, you could say, oh, let me have V1 as a source and V2 as a source, and write the equations. How would you solve that? Or how would you analyze this circuit? It's sort of begging to do mesh analysis, isn't it? We've got two meshes. Why don't we use something that we're comfortable with using? If we write a mesh analysis equation for the left mesh, so let's do now KVL at the left mesh. Now we just have to remember how those currents are oriented. They're not both going clockwise or counterclockwise. One's going opposite to the other. We have in the left mesh, we have minus V1 plus 1 times I1 plus 2 times I1 plus I2. Is that okay? That's just KVL, and you should be very comfortable with that at this point in this course. So we have minus V1 plus 1 times I1 plus 2 times I1 plus I sub 2, and that brought us back to where we were going, or where we started. We want to find or identify Z11, Z12, Z21, and Z22. Well, this equation has a V1 in it, and it has I1 and I2 in it, doesn't it? But the first thing we might want to do is say, well, how would we find Z11 in this first equation? We could find it if we set I sub 2 equal to 0 pretty easily. So if we set I sub 2 equal to 0, then if we could find a relationship between V1 and I1, we would have our Z11. Meaning now to find Z11, we need to find 4 of these parameters. Let's find that by this relationship. Let's go ahead and set I sub 2 equal to 0. If we do that, now we have minus V1 plus I1 plus 2I1 is equal to 0. or V1 is equal to 3I1 and Z11 is 3. Or Z11 we really found by taking the ratio of V1 to I1 when I sub 2 was equal to 0. And that ended up being 3. Does that make sense? There's Z11. Now you have 25% of the problem finished. What if we wanted to find Z12? Do the same strategy. We have the governing equation. If we now want Z12, what happens when we set I1 equal to 0? Now we have minus V1 plus, whoops, that was a 0, wasn't it? So we had 1 times 0 plus 2 times 0 plus I sub 2. Or V1 is equal to 2I sub 2. And that now allows us to say, oh, we've now found Z12. V1 over I2 with I1 equal to 0 will give us Z12, which in this case is 2. Questions on that? What about the other two parameters? Well, that worked so neatly for that one. Why don't we just write a KVL on the right-hand mesh? Now we have a minus V2 plus 3I2 plus 2 times I2 plus I1. That's our KVL for the right mesh. Now we have minus V sub 2 plus 3 times I sub 2 plus 2 times I1 plus I sub 2 equal to 0. And if we want Z sub 2, 1, then that's the impedance between I1 and V2. We can set I sub 2 equal to 0 in that relationship. And doing that, we now end up with V sub 2 is equal to 2I1. Or Z21 is now V2 over I1 with I sub 2 set equal to 0, and that's equal to 2. And finally, to obtain Z sub 2, 2, with that second mesh equation, we can simply set I1 equal to 0. And now we have minus V sub 2 plus 3I2 plus 2I2 is equal to 0. Or now we have Z sub 2, 2 is this V2 over I2 with I1 equal to 0, and that's now equal to 5. Meaning our Z parameters, if we wrote this as V is equal to Zi, which is really what it is, with V being a stacked vector, V1 over V2, and I being a vector, I1 over I2, the impedance matrix, or the Z parameters, are Z11, which hopefully was 3. The off diagonals were equal, and they were 2, and we had a Z22 of 5. And those are the 4 Z parameters for that T network. And those don't all immediately appear as separate elements in that circuit. We have a 2, that's what's common to the 2, those are the off diagonal, but then the others are really the sum of those two impedances seen by I1 and I sub 2 in this particular circuit. Let's get a different circuit. Suppose now that you are finishing this second circuits class, we need to be a little bit more challenged with the circuit analysis. This shouldn't challenge you too much. This shouldn't take you much more than a napkin to work. We now have R1, R sub 2, R sub 3, and let's say this is now beta V1 here, and that's, let's say, a controlled current source. Here's V1, here's V2, there's I1, and there's I2. And again, maybe what we're looking for are Z parameters. Independent of whether or not I ask for the Z parameters, if you had to analyze this circuit in terms of V1, V2, I1, and I2, do you have a feel for what you might try to do? What kind of analysis you might try to perform? Now that dependent current source is problematic if we tried to do KVL or mesh equations, isn't it? Because we don't know the voltage drop across that. So maybe we need to write KCL equations or node voltage equations, and we can now define some node voltages. Let's just call this one as V sub A, and that one is V sub B. And what we want to do now is simply write KCL equations at nodes A and B. At A, what's our KCL equation? I'll do the hard part. I1 is equal to. Now we know the algebraic sum, or currents in equal currents out. What's the current going vertical? And then we have a horizontal current. That should be comfortably derived for all of you, right? That shouldn't be a problem. What about the second node? Again, I'll do the most difficult part since it's late in the semester. I2 is equal to. Now we have a voltage controlled current source, but that's just given. That's beta V1, and then we have the horizontal current going in the other direction. So that's now VB minus VA over R sub 2. And I might sit down and put my feet up and say, oh boy, I'm feeling really good. Am I premature in that good feeling? What am I looking for? Z parameters, which are equations that should contain what variables? My equations were V1 is something I1 plus something I2. V2 is equal to something I1 plus something I2. Ah, those silly V sub A's and V sub B's. I got some extra variables in here, don't I? So I need to get rid of those. If I could rewrite V sub A and V sub B in terms of I sub 1 and I sub 2, I'd be in pretty good shape. And that's what I want to do. I need equations which contain I1, I2, V1, and V2. Consequently, I need to get rid of V sub A and V sub B. Or I need to rewrite those in terms of I1, I2, V1, V2. If I go back to this picture, this circuit, what do I know about V sub A and maybe V sub 1? They're exactly the same, aren't they? So I could have eliminated V sub A from the beginning, but here are some observations. One is that V sub A is simply V sub 1. Well, that was pretty easy. I can now relate maybe V sub 2 and I sub 2 to V sub B by finding that current for I sub 2. Meaning I sub 2 is equal to V sub 2 minus V sub B over R sub 3. And that now allows me to solve for V sub B. V sub B is now V sub 2 minus R sub 3 I sub 2. And now I'm in better shape. Now I have equations for VA and VB in terms of I1, I2, V1, and V2. So now I can rewrite those earlier equations. I can now say I1 is V1 over R1 plus V1 minus V sub B, which is now V sub 2 minus R sub 3 I sub 2 over R sub 2. That gives me one equation. This was simply the V sub B from before. And in that first equation, all I have are V1, V2, I1, and I2. And that's what I needed. My second equation, I sub 2, was beta V1. That was okay to begin with, but then I had a V sub B, which is just V2 minus R sub 3 I sub 2 minus V sub 1 over R sub 2, and that's my second equation. Now I have two equations with four variables, but I'm looking for z parameters, so I now need to find V1 and V2 in terms of something times I1, I2. If I look at this, hopefully you can see that I could start pulling out V1 and V2. I could put this into sort of a matrix structure, and you're all experts with that since you're in 310, right? This now says that I have some matrix times V1, V2 equaling some function of I1, I2 on the right. I can simply put all the i's on the right-hand side, and then I have another function down below for the second equation. I hope that's okay. Then I can simply invert that squiggle, that matrix, and I'll have my equation that I want. I now, if I invert this guy, I can now solve for V1, V2 and obtain my Z11. It might be a function of S, Z12 in the general case, and that's now going to be my Z parameters. I want to give you some fun, so I'm going to allow you to go home and do that tonight. And you can then verify that Z1 is R1 over 1 plus beta R sub 1. Z12 is the same. Z12 is the same. And with my track record today, these may not even be correct. So you can come see me in office hours to verify if you're not coming up with these equations or these formulas. Z21 is now R1 minus beta R1 R2 over 1 plus beta R1. And then Z22 is the most complicated of all. It's now R sub 1 plus R sub 2 plus R sub 3 plus beta R1 R3 all over R2 times the quantity 1 plus beta R1. And those are now our Z parameters for that circuit. And that circuit had a dependent source in it. But the process should have been clear as to how we derived it. We just started with some basic KCL equations. And that led to this result. That's now how to find the Z parameters if you're doing circuit analysis. What if you go into the lab and take some measurements? Can you now extract your Z parameters from some physical measurements? Let's now find two-port parameters. Finding two-port parameters from measured data. Suppose that we again want these Z parameters, and somebody goes into the lab and they say, oh, I'm going to open up port 2 and take some measurements. So port 2 is open circuited. That's just hanging. And I measure V1 to be 8 millivolts. I1 is 4 microamps. And I sub 2, the current, no, what is I sub 2? 0, isn't it? If port 2 is open, I sub 2 is 0. There's no current flowing, and so the only other variable that I can measure is the voltage across that output terminal, which suppose that that ends up being minus 8 volts. That's one set of measurements. I just opened up port 2 and took those three, measured those three values. Now what I'm going to do is I'm going to take port 2 and short circuit it. Now what's V2? It's 0 now, isn't it? So now I can measure the other three. V1, let's say, is 5 volts. I1 is 5 milliamps. And I sub 2 is 250 milliamps. Now you've already told me something about each of these two conditions for these two tests or for these two measurements to have occurred. With port 2 open, you've already told me that that gives rise to this fact that I sub 2 is equal to 0. And now we can go back to our Z parameter governing equations, put in I sub 2 equal to 0 into both equations and see what you end up with. For one, if we looked at the first equation, that's the V1 equation, we can now find or solve for Z11 using these variables. Z11 is simply V1 over I1 with that output port open circuited, or with I2 equal to 0. We measured V1 to be 8 millivolts. I1 was 4 microamps. So that this ends up being 2K ohm for Z11, or 2,000 ohms. We can also, with I2 equal to 0, or with port 2 open, we can also find or solve for Z21. That's the ratio of V2 to I1 with I2 equal to 0. And this one, if you go through, ends up being a minus 2 megohm. That's Z21. Then we have our second set of measurements with port 2 short-circuited. That now implies that V sub 2 is equal to 0. And now we have a little bit more interesting algebra, maybe, but we could now say, okay, V sub 2 is Z21 I1 plus Z2 sub 2 I sub 2. And we've already found this guy from before, haven't we? Z21. So that now we can solve this for Z sub 2, 2. This now is equal to 0, and we now have minus Z21 I1 over I sub 2, and that ends up being with the measured values for I1 and I2 with the short-circuited second port, or port 2 short-circuited. This is now 40K for Z22. And we could also go back to our first equation. We now have Z11 already determined. We have I1. We don't have Z12, but in that second set of measurements, it really doesn't matter what V2 is. We can now use I1, I2, and V1 to solve for Z12, and Z12 ends up being minus 20. And those are now our Z parameters from a collection of experimentally measured values. We've now found Z parameters by analysis. We've found them by measurement. Now let's use those if somebody now built up a circuit around a 2-port, or what might be referred to as a terminated 2-port. We now hang a load on V2, and we maybe put an input into the input terminals. We now are going to be looking at terminated, or a terminated 2-port network. For example, here is our 2-port. With the appropriate V1 and V2, I1, and I sub 2. What we want to do is terminate that, meaning we now want to hang a load onto the output side, Z sub L, some impedance, and we want to drive that with some source that might have a source impedance, Z sub G. And there's a lot of different things that we might be interested in relative to this particular interconnected circuit, a terminated 2-port. Somebody might say, well, what's the input impedance looking into those 2 ports? Or what's the output impedance looking in from the output? Or somebody might say, what's the gain between V sub G and V sub 2? Or what's the amplification of the current between I sub 1 and I sub 2? And we need to find ways of relating those particular parameter values to those desired quantities. What do we know on the left-hand side in terms of relationships between? What we are trying to do is actually find relationships for these voltage gains, current gains, output impedance, input impedance in terms of V sub G, the Z parameters, Z sub G, and maybe Z sub L. We might like to know, how do we relate those to maybe the voltage gain between V sub G and V sub 1? What we can do is we can identify some governing relationships. On the left-hand side, well, we know if we have Z parameters, we know that we have this. We know we have V1 is Z11 I1 plus Z12 I2. And we know V sub 2 is Z21 I1 plus Z sub 22 I sub 2. But what else do we know? We also know how V sub G, V1, and Z sub G are related by the left-hand side. We can now say that over on the left-hand side, we have minus V sub G, just doing a KVL. If I do a KVL, don't let me set that equal. Let's now say that's plus Z sub G I1 plus V sub 1 is equal to 0. What about if we did something similar on the right-hand side? Well, now we can relate V sub 2 to I sub 2 and Z sub L. That's just Ohm's law generalized, except I sub 2 is going in the opposite direction we would normally think of in terms of the passive sign convention. So now we actually have V sub 2 is equal to minus Z sub L I sub 2. Is that okay? So now we have 4 equations. And we might want to find, let's say, the input impedance. Or we might want to find the voltage gain. Or we might want to find the current gain. There's all sorts of things we might want to be doing with this terminated 2-port. Suppose we wanted to find Z sub I. And these relationships are all cataloged in one big table in Chapter 18. Let's just show where one of those maybe of the many different possibilities comes from, or how we might derive that. If we wanted to find the input impedance Z sub I that we had just defined, Z sub I is just V1 over I1. That's Z sub I, or Z sub n. That's V1 over I1. And we want to now try to find a relationship for Z sub n in terms of our Z parameters, Z sub G, Z sub L, and V sub G. Those are the parameters we want to use. So now what we want to do is try to get rid of some of these I1s and I2s, V1s and V2s in this relationship. Looking at equation 2, or let's start with equation 1. Let's try to eliminate I sub 2 from equation 1, since we really want V1 over I1, and we have V1 and I1 there. If we could just get rid of or rewrite I sub 2 in terms of some of these other parameters, V sub G, Z sub L, and Z sub G. So let's now try to eliminate the I sub 2 variable from equation 1. To do that, we're going to do it in stages or in steps. We're going to actually start trying to use equations 4 and 2 to find another form that will relate I sub 2 and I sub 1. Do you see that we have a V sub 2 here and a V sub 2 there, so I can get rid of V sub 2, and now I simply have I sub 2, I1, and I sub 2 in one equation. I can now solve that I sub 2 in terms of I sub 1, plug that back into equation 1. That's where I'm headed. Is that making any sense? Let me try to write that down. I'm trying to eliminate I sub 2 from equation 1, and one of the first steps in doing that is I'm going to use equation 4 in equation 2 and solve for that I sub 2. And what it will be in terms of is simply I sub 1, and that's a good thing. Well, we had V sub 2, which was minus Z sub L I sub 2. That was equation 2's left-hand side. But that's equal to Z21 I1 plus Z sub 22 I sub 2. This was just V sub 2, right? And now we have an equation that just involves I1 and I2. Now we can say from that I have minus Z21 I1 is equal to Z sub 22 plus Z sub L times I sub 2. Or I now have I sub 2 is equal to minus Z21 I1 over Z sub 22 plus Z sub L. Now I can use that relationship to eliminate I sub 2. Doing that, I now have V sub 1 is equal to Z11 I1 plus Z12 times what I just derived, which is minus Z21 I1 over Z sub 22 plus Z sub L. Or this is now Z11 minus Z12 Z21 over Z sub 22 plus Z sub L times I sub 1, and that's equal to V1. And that's now going to give me my input impedance, Z sub I. Z sub I is now V1 over I1, so I divide both sides by I1, and I'm left with Z11 minus Z12 Z21 over Z sub 2 plus Z sub L. And that might be one of your expressions in that big table that relates your input impedance to a terminated two-port in terms of Z parameters, load impedance, and potentially input voltage and input impedance. But in this case, we didn't need the input voltage. We're looking for the input impedance, didn't we? That concludes chapter 18. That gets us to the end of the book. And I will see you, if not sooner, I will see you in in a week, isn't it? Today's Tuesday. A week, but much sooner. 10:30 is your final on the 17th. Good luck with your finals.